It's good, code milkers. Today's video is gonna be quick. I've solved the problem. I've got somewhere to be, so I'm just gonna record this quick, go over my solution, and call it. Today's problem was jump game, and given an array of non-negative integers, you are initially positioned at the first index of the array. Each element in the array represents your maximum jump length at that position. So your job is to determine if you are able, from that first index, to reach the last index of the array. So if you think of each element of the array as a potential jump, can you reach the end of the array starting from the first element? So we have an example here. We have our input, and this one returns true, because I'll explain the rationale here. If we start at 2, that means that we have a potential 2 index jump or 1 index jump. So that means we can either land at 3 or 1. If we land at 3, that means we have either a 3, 2, or 1 jump. If we jump 3, we end up right at the last index. So we're good. The second one returns false, because as you'll see, if we start at the first index, which is 3, if we jump 3, we end up at 0. If we jump 2, we end up at the element 1. And if we jump 1, we end up at the element 2. Now from any of these spots, no matter what jump we make, we can't reach the last index. Because for 2, if we jump 1, we only get to 1, and we can only go to 0 after that. If we jump to 0, we can't jump with a 0. We got no jump game there. So it just ends there, and we can't jump from the first index to the last one, so we return false. Now, my solution is a little unintuitive in that you start from the end of the array and work towards the front, and then go through a stack of the indexed elements and determine if the current element can reach the next index based on its value in the array. So it's a lot to take in. Let's look at it here. So let's look at that example we have above, 2, 3, 1, 1, 4. Okay. Now if we're starting from the back, so the end of the array, we don't need to include 4, the last index. So we're going to start at 1. So 1 is index 3, and its value is 1. With that 1 value, can we jump to the end of the array, which is index 4? So we're going to do 3, the index, plus 1 equals 4. Okay, good. So we're going to put this in a stack. So we're going to put the index 3. Okay. Next element is 1. This is index 2, and the value is 1. Now, this is where it gets a little different. Can it either land at the end of the array, or can it land on the topmost element in the stack? So we'll see that with a 1, we can go to index 3, no problem. So we push it onto the stack, which now the most top element is 2. Now we go to 3. This is index 1. Its value is 3. So can we jump from 3? Can we jump from the index 1 with the value 3 to the end of the array, which is index 4? Yes, we can, because 1 plus 3 is greater than or equal to 4. So we can actually get to the end here. So we're going to push that onto the stack as well, the index of it, because that's how we're going to access the value from the array. And then last, we do not need to include the first element, because that's where we're going to start the next part of this. So now we're going to work our way through the stack. We're going to start at the first element, 2. So we're at index 0, we're at value 2. Now we look at the topmost element of the stack. Is the index at the topmost element reachable from the current index 0 with the current value 2. From 0, we can get to 1 because 0 plus 2 is greater than or equal to 1. So we set the current element equal to the next index and pop it from the stack. So now we have 3 and 2 left. Now our current element is 3 with the index 1. Can we reach the next index in the stack, which is the topmost element in the stack, using the current element's value plus the current element's index? Yes, we can. From index 1, we can reach index 2, no problem, because it's greater than or equal to 2. 3 plus 1 is greater than or equal to 2, so we can make a jump. So now we pop the stack and we get 2, which is our new current element, and that means we have 1 left in the stack. Now we have what's our next one? We got 3. Yep, index 3, which is 1. And can we reach the topmost element in the stack with that given index value combination? We can. So we get 4 here. Wait, I think I missed one. Yep, this is 1 and 2. This is 1 and 2. I skipped one index. Okay. 1 and 2. And that puts us at index 3 because we popped the last remaining element from the stack, which means our stack is empty. Now we have to look at our value 1 at index 3. Using that index value combination, can we add to the current index 3 to get to the end of the array 4? 3 plus 1 is greater than or equal to 4, so it's true. So this is how it's done. The time complexity, I'm pretty sure, is O(n plus n). It might be a little less than that, but that's roughly what it is because we go through the array once from the end to the start, and we go through the stack from the start to the end, basically. It might be n plus n minus 1 because we don't include the last element, but those are little details that the time is roughly the right one. Here's the implementation. We initialize our stack, and then we are saying to push the current index onto the stack if either of these conditions is true. That the current index plus the current value at the current index is greater than or equal to the length of the array, minus 1, because we're talking about indexes here, or the current index plus the value at the current index is greater than or equal to the last element on the stack. So long as we can reach the next element, the next valid index, we might be able to reach the end of the array. Hope that makes sense. Basically, this question boils down to figuring out what are the good indexes and the bad indexes. The good ones are ones that either you can jump to the end of the array or to the next good index. So that's why we start from the end and work towards the front, because the first good index is the one that you can jump to the end of the array from. Then here we're doing the actual linear pathing from the front of the array to the end. So we start at 0, and we just have an arbitrary true here. While this is true, the loop is going to break itself when it's necessary. So if the sum, which is the current index plus the current value at the given index of nums, if the sum is greater than or equal to the indexed length of nums, then we know we've reached the last integer or element in nums, which means that we have jumped from the beginning to the end, which means we're good. Return true. if sum is greater than or equal to the last element on the stack, so the topmost, that means that we can jump from our current index to the next good index, which puts us one step closer to the end of the array. So in that case, we just pop the stack, reassign current index, and continue on our way. And if either of these is not true, we just return false. That means that the indexes have stopped being good. I know it's a lot to take in. This is a hard problem. I hope my solution helped. I'll just run it here so you can see the time complexity. We've got, how many percentages did we beat? Oh, 92%. It's not bad at all. It was a lot lower earlier. It was like 30%. So I'm surprised to see it say 92. Have a great day. Hope this helped.